So for our next example of divide and conquer, let's look at a very simple problem that we learnt in primary school, how to multiply two integers. So the way we multiply two integers is to form these partial products. So when we have two multi-digit integers, here we have two-digit integers, we first take 3, right? So we are multiplying x by y. So we take the units digit of y and create this product of the units digit of y multiplied by all of x. Then we shift by 1 to account for the 10 factor, and then we take the tens digit and again we multiply. So we form one more partial product, and then we add up these partial products, right? So we add up these partial products and this gives us the actual sum. So we have to add these. So depending on the number of digits, we will have as many partial products as there are digits in the second operator in second number in y, and we will have to add up that many partial products. Now this is not specific to decimal multiplication that we have seen here in base 10. The same thing would work if we transform this same problem or any problem to binary. So for example, this is 12 in binary, so this is 8, 4, 2, 1, right? So the top number is 12 in binary and the bottom number is 13 in binary. So if we multiply 12 by 13 in binary, then 1 times this thing is 1100, 0 times this thing is all zeros, and again 1 times that is 1100, 1100, and now we have to add up these partial sums. So the usual way, now you can see that we have a stack of partial sums to add, right, partial products to add. So we don't really want to do a kind of long addition this way. So the usual way is that we maintain this cumulative sum. So we will take these two and we will create an intermediate sum which says 0, 1, 1, 0, 0. Of course, the leading 0 we do not have to keep. Then to this we will add 1, 1, 0, 0 at this point, and we will get 0, 0, 1. So I think so we will add, so this will come to the left, so 1, 1, 0, 0, and so we will get 1, 1, 0. So in this way we will just keep adding these sums as we go along, right? So we will get these cumulative sums. So how long does it take? Well, each partial product requires me to, let's assume that both the numbers have the same length, so they are n bits. So each partial product requires me to process n bits to come up with this number. So that's an order n operation, right? And then I have to add two n bit numbers. So that's another order n operation. So I do this n times, one for each partial sum, right? And so overall I get an n squared algorithm. So this is our naive multiplication algorithm, the way we learnt it in school, right? And this is an n squared algorithm. Now the question is it possible to do any better than this? Because after all, in general we can't do away with any of these intermediate values, right? So it seems logical that every row, so here of course we get some zeros, but that also helps us to shift. If you are doing it in binary, it looks like this row is not required, but what if it was there? We would have to add it up, right? So in the worst case, if everything on the bottom was 1, every row would be required. So it does look like all these n squared operations are needed. We will get n partial products and we have to add them up 2 at a time. So we have to end up doing n squared work, or so it seems. So for divide and conquer, we need to divide something. So usually we have been taking a list or a sequence of values and dividing it into parts, right? This is what we did for things like merge sort, and we have also done that for other things. So even for counting inversions, we counted the first half and the second half, and then we combined across them and so on. So even for counting pairs of points, the closest pair of points, we divided the points into those to the left of the separator, the right of the separator, and then we combined them. So we need some way of splitting up. And what is a logical thing to split up? Here n is the number of bits. So the logical way to split is to take half the bits and do them separately and half the bits and do them separately. So this is what we are doing here. So we are saying that if we take an n bit number, it has bits, the lowest bit, usually the lowest order bit, that is the units bit is usually b0, and the highest bit, which in this case in powers of 2 represents 2 to the n minus 1. So this is bn minus 1, right? So 0 to n minus 1 are the n bits. So we are going to split it halfway, right? So we go from 0 to n minus 2 by 1, n by 2 minus 1, and then from n by 2 to n minus 1. So we will call the upper part of, so remember we are multiplying x times y, right? So we want to find the product x times y. So we will split x this way. So we will take the lower half of x and call it x naught, and we will take the upper half of x and call it x1. So x naught is the last half in terms of the bits or the digits, and x1 is the first half, and similarly we have y0 and y1, right? So now what is the number actually? The number actually is this plus this amount shifted by the appropriate power of 2, right. So, I can think of x as being x1 times 2 to the n by 2. So, 2 to the n by 2, right, is just 1 with that many zeros, right, n by 2 zeros. So, if I now multiply x1 by that, it gets shifted to the left, and then I am just adding these two and getting an n bit number, right. So, I have 2 to the n by 2 times x1 plus x0, so this is x, and this whole thing is y. So, x times y can be equivalently written in terms of these 4 smaller numbers, right, with an appropriate multiplication to make the scaling correct, but that multiplication is not a real multiplication. This is, I do not have to do any serious multiplication, this is just bit shifting. So, if I was working in decimal, this is like multiplying by 10, and I multiply by 10, I do not have to do any real multiplication, I just have to stick a 0 at the end. So, I just multiplying by an appropriate power of 2, which shifts it to the left by that many zeros. So, now if we expand this out, right, then we will get x1 times y1 times 2n by 2 to 2n by 2. So, I get x1 times y1 times 2 to the n. On the right I get x0 times y0, so x0 times y0, and then I have these two terms, right. So, I have x1 times y1 times 2 to the n by 2, and I have x0 times, sorry, I have x1 times y0 times 2 to the n by 2, and I have x0 times y1 times 2 to the n by 2. So, I have these two cross terms, okay, which are shifted by n by 2. So, I have the leading term x1 y1 which is shifted by n bits, I have the two cross terms which are shifted by n by 2 bits, and I have the last term, the units term in some sense, which is just x0 times y0. So, I multiply this way, I multiply this way, and I multiply these two ways, right. So, this gets shifted by 2 to the 0, this gets shifted by 2 to the n, and this gets shifted by 2 to the n by 2. So, in other words, I do 4 smaller multiplications, right. So, I do 4 multiplications of these split numbers which have half the number of bits. So, in order to multiply two n bit numbers, I am replacing it by the problem of multiplying 4 n by 2 bit numbers, right. So, 4 times I am doing an n by 2 bit multiplication, and I am achieving my n bit multiplication through that. So, this is a naive way of approaching this divide and conquer thing. So, this corresponds to the combine step, right. So, the division step would be to actually extract these two sections by bit shifting. So, remember, if I just shift right, I will n by 2 times, I will get the upper half and the remaining part will go off, and if I shift left, I will get rid of the other thing, right. So, that is how we get this. So, it is like multiplication and division and remainder. So, our recurrence now says that if I have to multiply two 1 bit numbers, it is just a constant amount of work. So, T of 1 is 1, and if I have to multiply two n bit numbers, then I have to instead multiply 4 n by 2 bit numbers, which is what I have done here, and I have to spend order n time. Now, one reason I have to spend order n time is I have to do this addition. So, remember earlier when we did partial products also, we said that each addition of two n bit numbers will take order n time. So, here we are adding two n by 2 bit numbers, but that is still order n, right. So, combining the partial product requires me to add these order n bit numbers. So, that is why the combination term actually requires order n work. So, if we try to solve this recurrence, right, by the usual way that we have been solving so far, what we will do is we will take this T n by 2 and we will expand it, right. So, we will say that T n by 2 by the same recurrence is 4 times T n by 4 plus n by 2, and then if I group these terms, I get 4 squared, right, and I get 4 times n by 2 is 2, so I get 2n plus 1, so 2 plus 1n, right. If I do it one more time, then it pattern becomes a little clearer. I get 4 cubed here, I get 4 squared, and again I am expanding this, right. So, I get 4 squared times 4 cubed times T n by 2 cubed, and then this 4 squared and 2 squared will leave me with a power of, will leave me with 4, which I can write as 2 squared. So, I have 2 to the 0, 2 to the 1, 2 to the 2 after 3 steps, right. So, in general after k steps I will have k minus 1 here, and I will have k here, and I will have k here. So, as we know, we want to go until we hit 2 to the k is equal to n, which is basically k is log of n. So, at log of n I have 4 to the power log n, I have T n by 2 to the power log n. So, this is just T of 1, right. And then here I have this telescoping sum 2 to the power 0 plus 2 to the power 1 plus 2 squared up to 2 to the power log n minus 1, right. And this whole thing, right, is actually going to be approximately n, because it is going to be approximately 2 to the power log n minus 1. So, this is going to tell us that this thing, we will look at this again a little later more carefully, but essentially what we find is that by doing this naive divide and conquer, we have not really progressed, because we have got again n squared, which we had got even by our high school or primary school method of doing it digit by digit and adding up the rows, right. So, by rewriting this in this form, we got this recurrence Tn is 4 Tn by 2 plus n, and this was order n squared. So, it appears that divide and conquer really has made no progress in terms of improving the complexity of this multiplication problem. But it turns out that we just have to be a little more careful about how we compute the terms that we need in our final answer. So, this is an algorithm due to Karatsuba. So, what Karatsuba said is, let us compute something which is not directly required in my answer above. So, let us look at this sum, this product x1 minus x0. So, remember that x is written as, the upper half is x, okay, and y is written as y1, y0. So, I am going to take the lower part of x and subtract it from the upper part of x, x1 minus x0, and multiply it by the lower part of y, y0, subtracted from the higher part. So, so this looks like a strange quantity to multiply, but the reason we are doing this is because it yields some interesting terms in its expansion, right. So, again we get x1 times y1, then we get plus x0 times y0, because both two negatives cancel, and I have two negative terms, minus x1 times x1 times this thing, the two cross terms, and minus x0 times, right. So, this is the multiplication of this thing. So, the point to note here is that the terms that we really need are hiding inside this. So, now we have achieved this by multiplying two n by 2 bit numbers, because remember that x0 and x1 were half the length, right. So, if I started off with n bits, these are all half the length. So, this is a n by 2 bit multiplication, just like as we were doing in the earlier divide and conquer. Now, I want to compute these two explicitly as we were doing before, right. So, x1 y1 and x0 y0. So, I have now done 3 multiplications, and now I need to extract this bit. But this bit is easy to extract now, because I can just take the sum of these two and subtract this whole thing, right. So, if I take the sum of these two and subtract this whole thing, then what happens is in the subtraction, these two terms cancel, right, and so I am left with plus x1 y0 plus x0 y1, which is what I need. So, in other words, this term I can get by just subtracting cleverly, adding and subtracting cleverly the result of the 3 multiplications I have done. Right. So, the crucial thing is that instead of doing 4 multiplications, which I did in the naive case, I have brought it down to 3 multiplications. So, in order to multiply 2 n bit numbers, I now only have to do 3 multiplications of n by 2 bit numbers, and then do some clever rearrangement to make it work, right. So, let us just look at the algorithm before we do the analysis. So, we are saying that let us just keep track of the number of bits. So, we are multiplying x and y, which are 2 n bit numbers. So, the parameters that our algorithm takes are the 2 numbers and the number of bits, right. So, if the number of bits is 1, then we just return the product. So, this is just a trivial case, this is the base case. Otherwise, we are going to split it. So, we compute the half the number of bits, right. And then the way we split it, this is actually, we say, as I said, is bit shifting, but you should think about x1 as x divided by 2 to the m. So, I start with x, right, and if I divide by 2 to the m, all this part gets cancelled off, right. So, remember, if you divide by 10, what happens, right, 22 by 10 goes to 2.2, and then if you drop the fraction, it is 2, or 27 by 10, for example. If I take 2734 divided by 10, right, I get 273 by 0.4, and if I drop this and I divide by 10, I get 27.3, and I drop this, right. So, I am just shifting right and dropping the decimal point, but it is actually dividing by that appropriate power of 10. If I want to take the top, remove 2 digits from my number, the rightmost 2 digits, I divide by 10 squared. So, if I want to remove m bits from my number, I divide by 2 to the power m, right, and the remainder, if I, after the division, is what I get as the lower bits, right. So, x0 is x mod 2 to the power m. So, that is the remainder. So, this is division and remainder, but really, because I am doing it with respect to this power of 2, it is just a question of shifting bits. So, this does not really cost anything. Okay, this is a simple operation. I am not really doing a arithmetic division, it is really bit shifting. And then finally, I need to create this intermediate quantity which I want to multiply. So, I will just set A to be the left hand side of that and B to be the right hand side of that. So, I need to multiply x1 and y1, I need to multiply x0 and y0, and I need to multiply this subtraction x1 minus x0 by y1 minus y0. So, now I have set up all the things that I need. So, now I do my 3 recursive multiplications. I multiply x1 by y1, so I will get this term, right. I multiply x0 by y0, so I will get this term, right, and then I multiply a by b, so I will get this term. So, these are the 3 terms that I need, and I will call them p, q and r. And how do I multiply them? This is divide and conquer, right. So, I pass the arguments to the same algorithm, it is recursive, but with half the number of bits. I am using m bits instead of n bits. Remember, m is n by 2. And now when I get the answer back, right, I know that the highest order term is p, the lowest order term is q, and the intermediate term, which has to be multiplied by 2 to the power n by 2, is given by this clever expression of Karatsuba. It is this p plus this q minus this r. Right. So, I can compute that intermediate thing, which should be x1 y0 plus x0 y1, by just taking the sum of the 2 higher and lower order products and subtracting this complicated product, seemingly complicated product, right. So, this is how Karatsuba's algorithm works. So, what we have effectively achieved is that we have taken this 4 and made it 3, right. So, the question is, what does that buy us in terms of complexity? So, let us try to analyze Karatsuba's algorithm. So, what Karatsuba's algorithm says is, unlike our naive thing which had 4 t n by 2 plus n, we have 3 t n by 2 plus n, right. So, the base case as always is when I have 1 bit is 1, but when I have n bits it is 3 times t of n by 2 plus n. So, we do our usual expansion trick, right. So, I will expand this thing, right, and what I get is 3 times t n by 4 plus n by 2, right. And if I rewrite this, I get from this 3 times this 3, I get 3 squared. I can rewrite 4 as 2 squared, right. And now I have a 3 times n by 2. So, I have a 3 by 2 and I have the original 1. So, 3 by 2 plus 1 times n. So, if I expand it once more, the pattern becomes a little clearer, right. So, if I now replace this quantity using n by 4, then I will get n by 8, which I will write as n by 2, 3 times t of n by 8, right, and n by 2 squared, because that is what I passed. And now if I look at this, I have this 3 squared divided by 2 squared, right. So, I have this 3 into 3 squared, 3 cubed coming here. So, this is 3 and this is 3, this goes with the number of times I have expanded. And here I have this again telescoping sum, but now the telescoping sum, earlier it was 1, 2, 4, 8 and so on. Now it is 1, 3 by 2, 3 by 2 squared. So, earlier it was 1, 2, 2 squared, right. So, that telescoping sum has come to 3 by 2 because I am only creating 3 copies instead of 4 copies. So, if I keep doing this, right, after our usual thing, when we bring down this thing to 1, I would have done this log n times. So, then this 3 would have become log of n, right. So, I have just written 2 here, but you do not have, it is always 2, right. So, I have 3 to the power log n, and this has again expanded 3 by 2 to the power log n minus 1. So, we have to now analyze this messy expression to find out what it means, right. So, first thing we can do is we can kind of eliminate this thing, because this is just 1, right, and then we are just looking at this expression at the bottom. Now, this is a geometric series, right. So, form a plus ar squared plus, so it is where each term is multiplied by a constant factor r with respect to this, okay. So, in our case r is 3 by 2, right, and in the geometric series formula is usually, if I have n terms in my formula, it is r to the n, one of the formulas is r to the n minus 1 divided by r minus 1 times a. Right. So, this is a formula. So, I am just applying that formula, right. So, 3 by 2 is my ratio, so that is my r. So, 3 by 2 minus 1 is in the denominator, and 3 by 2 3 by 2 to the number of terms in my thing is in the numerator, okay. So, Now let us look at this term, right. This is of form 3 to the log n. So in general, if I have a to the log n, I claim it is the same as n to the log a, right. So the reason for this is if I take a to the log n and say that this is some value z, right. If I take now log on both sides, I get log of a to the log n is equal to log of z. But remember that when I take logs like this, I can bring that down. So this is the same as saying that log, I can bring this exponent down. So I can say this is the same as log of n times log of a is equal to log of z. And now I can interchange the roles, right. So I can, instead of thinking of this as having been the exponent, I can think of this as having been. So I can think of this as log a times log n is equal to log z. I just interchange the order, and this is the same as saying that log of n to the power log a is equal to log z, right, which is the same as saying that the original z I was trying to compute is also n to the power log a, right. So if I have a to the power log n, I can interchange and say it is n to the power log a. In general, if I have a to the power log of anything b, this will be equal to b to the power log of a, and it does not matter what the base is. This could be, in our case, base 2, but it could be any base, right. So this is true in general. A to the log b to the base c is equal to b to the log a to the base c because of this way that the logs interact with each other. So therefore, this 3 to the log n is just n to the log 3. What about this thing? Okay. So this thing requires a little bit of work, but basically the important thing is this and this term, right. This is the only term that matters, everything else is going to cancel out. So n times 3 by 2 to the log n, that's what we want to worry about, right. But now if I use the expression above, I can interchange the n and the 3 by 2 and say this is the same as n times n to the power log 3 by 2. So I have just swapped these two using the thing above, right. I brought the n down and put the 3 by 2 in the exponent. But log 3 by 2, log of x by y is log x minus log y. This is how logs work, right. So the log of a division is the subtraction of the logs. So I get that this is n times, and this numerator becomes log 3 minus log 2. But what is n? N is just n to the power 1, right. And what is log 2? Log 2 is just 1. So I have n to the power 1 and this thing is just 1. So I get n to the power 1 times n to the power log 3 minus 1, right. So now I have a multiplication of two things, so I just add it up, right. So I get n to the power 1 plus log 3 minus 1. So again I get n to the power log 3, right. So both this term and this term are actually giving me n to the power log 3. So this is going to be my final answer. My final answer is that this t of n is actually n to the power log 3. Earlier, remember that we were looking at n squared. So what is the difference between n to the power log 3 and n squared, where log 3 is actually something like 1.59. It's of course a irrational number, but if you round it off to 2 decimal digits, it's 1.59, which is significantly less than 2, right. So I have come down from n squared to n to the power 1.59 by doing this clever Karatsuba divide and conquer. So if we do a naive divide and conquer, we got no benefit. But then if we look at that naive divide and conquer and we look at the structure of the terms that we need to reconstruct the answer, it turns out that we can replace 4 multiplications by 3 multiplications and do some more clever combining to get the answer. So this algorithm has an interesting story behind it. So let's just look at that. So Andrei Kolmogorov, you may have heard the name, is one of the towering figures of 20th century mathematics. He has contributed to numerous disciplines. Most areas have some influence of Kolmogorov. So Kolmogorov in the 1950s conjectured that multiplication could not be done in less than quadratic time. So this was a public conjecture of his, and in fact he ran a seminar in Moscow University in 1960 where among other things he stated this conjecture. He said this is a conjecture which I believe should be provable, but I do not have a proof of it. So he stated it as one of the problems that could be addressed among the various open problems that he discussed in the seminar. So there was a young student in the audience, our friend Karatsuba, Anatoly Karatsuba. He was a 23-year-old student. So he was struck by this claim that you cannot do multiplication in less than n squared time, And he thought about it, and 2 weeks after Kolmogorov mentioned it in this seminar, remember that Karatsuba had not thought about this problem before until he was introduced to it by Kolmogorov. Two weeks later, he had come up with this clever idea, and he presented it to Kolmogorov, and Kolmogorov, of course, immediately realized it was correct, and then in the next seminar he announced it, and then that was the seminar. The seminar was just the announcement that this conjecture had been settled in the opposite direction to what Kolmogorov thought it would be. So a small aside on this is that Karatsuba actually used a slightly different formulation from what we use. So instead of our formulation of this subtraction, so remember we used x1 minus x0 and y1 minus y0, he used x1 plus x0 and y1 plus y0, right? And this just changes the thing. So in our case, what we did was we took the two terms x1 y1 plus x0 y0 and we subtracted that r, right, so that we got the right thing. Now instead you take r and subtract that and the same thing happens. These two things will cancel, and because these are already positively occurring, these side products are already positively occurring, they will remain. So you just reverse the order of the subtraction of the three terms, right? Instead of subtracting the complex term from x1 y1 plus x0 y0, you do it the other way. So what is the difference? Well, the difference really is that this sum is the sum of two n-bit numbers. And now when you sum two n-bit numbers, as you realize, the highest bit could generate a carry. And if you have a carry in the highest bit, then that n-bit number plus n-bit number generates an n plus 1 bit number as a sum. So technically your recurrence doesn't involve something which is half the size, but something slightly more than half the size it could involve, right? So instead of t n by 2, you are saying t n by 2 plus 1. And that becomes a little messy to calculate. So the analysis becomes rather messy if you use Karatsuba's thing. It still works, but you have to be a little more sophisticated about the way you do the counting. So the person who actually came up with the simplification that we have used here was Donald Knuth, who is again a towering figure of computing, if not mathematics, from the 20th century, and continues to be a towering figure. So Donald Knuth realized that you can actually subtract instead of add. Now when you subtract, you do not have a problem. If I subtract one n-bit number from another n-bit number, it only becomes smaller, it cannot become bigger, right? And then you can use, as we saw, the rearrangement in the other way to still recover the missing terms that you need for the final sum. So this is the history really of Karatsuba's algorithm and the presentation that we have used in this lecture, which is actually a reformulation due to Donald Knuth to make the analysis go a little more smoothly. Now we have done this whole thing in binary just to be simple about talking about bits, but you can actually do this in any base. So if you do this in base 10, it is the same, right? As long as you know how to multiply two digits in 1 unit of time, you can take a base 10 number with n digits and divide it into two groups of n by 2 digits, and everything is precisely the same. You can do it in base 16, you can do it in base 4, right? So it really doesn't matter what base you are working it, you are just saying take the digit sequence in that base and divide it by 2 and everything works, right? So that is Karatsuba's algorithm for integer multiplication using divide and conquer.